you for the introduction and also to the organizers for the invitation to this very nice conference, I have to say, super well organized. And today we'll talk about a joint work with Maximilian Nitschner from the University of Science and Technology in Hong Kong. And it is about bulk deviations for the simple random walk. And you will see it will have to do with random interlacements a little bit, actually quite importantly. And let's see about the range of the random walk, it will bring in capacity and so on. So it should be nice probably. Okay, let's start. So let's start with the simple notation, let's say. So we have the simple random walk on ZD. Okay. We are interested in looking at the occupation time field of the simple random walk. So this is the amount of time that the random walk spends at every site on ZD. As you will see quickly, the dimension we are interested in is greater or equal than 3. And then we want to look at some observables of this local time that are local observables. So we have a range of inspection for the local time field and a local function f of my occupation time field, which we assume to be non-decreasing and positive and with sublinear growth or bounded, you can think about. So we have this observable here, and we look at this local function of the field inside a model, inside a big macroscopic set, the n, which is just modeled after this model shape D, which is a subset of my RD. And then it is just about this quantity here, which is some behavior of the bulk for the occupation time field of the simple random walk locally in these boxes. Let me make a few examples for the choice of this function here so that it makes it a natural object to look at. So suppose that the range of inspection is just 0, so we look just at each point of my set Dn. Then this big average that I wrote is just going to be the fraction of, the fraction of points that are visited by the simple random walk in this big macroscopic object Dn. Okay. If I take f of L to be just the local time at the point 0, so I evaluate this function and it is just giving me the local time in 0, then if I look at this, that big average, this is just the total time spent by the simple random walk inside this macroscopic set, Dn. And so on, and then we have maybe a bit more interesting examples. One could be the random walk sausage, so the number of points covered by the random walk sausage of size R inside of Dn. And one a bit more interesting in terms of percolation is the following. So we look at the number of points that are not in a connected component of size R in Dn without the range of the random walk. Then you could imagine in this example to take, so eventually what you want to do is to take R to infinity, and so here I will give you the number of points that are disconnected by the simple random walk from infinity. Okay. So these are the kind of functions we are interested in, but of course the setup is pretty general and we can treat many functions. Okay. So as I said, you just think about taking R to infinity, and this last function here, this last observable, really gives you the fraction of points in the end that are disconnected from infinity by the simple random walk. So we are interested in deviations, in large deviation estimates for this big average here, and these are the so-called bulk deviations. Of course, we will look at the dimension bigger or equal than 3 Because as we know, in a set or in a box of diameter n, the amount of time that the simple random walk is spending inside is n squared. Here we are dividing by n to the d, so this quantity as n goes to infinity goes to 0 in dimension 1, in dimension greater or equal than 3. So this is going to be a rare event. While in dimension equal 1 and 2, it's not interesting as the random walk is recurrent. In fact, for the rest of the talk, just to make all the notation simpler, we will just focus on the simple observable, that is the function f of L, the indicator of L0 being greater than 0. And so we will just look at the fraction of points covered by the simple random walk inside this macroscopic set, dn, and we will look at large deviation estimates for the probability that the random walk covers a macroscopic fraction of this set. So the basic question is a large deviation question, and we look for exact asymptotic rates. Okay, so the goals of the talk are the following: estimate the large deviation event, and in doing so, we will learn in a way, as it is usual in large deviations, what is an optimal strategy for the random walk condition on this event happening. What is the strategy that the random walk needs to use in order to make this rare event happening. Now, if you think about it, if we want to cover this big set for a macroscopic fraction, then our random walk that lives in ZD with D bigger or equal than 3 lives in a transient space, so it doesn't like to stay inside this set. So it needs to come back many, many times. Okay. So we are in a situation where there are some atypical high densities, and the geometry of what the random walk sees is locally transient. But globally is recurrent because it wants to come back many times. And this is really the situation where we see random interlacements. So the random walk, in order to achieve this deviant behavior, will look like random interlacements with a certain intensity. And this will be a pivotal important tool in the derivation of exact asymptotic rates for the bike deviations. Well, a first answer, which is non-asymptotic, but it still gives the right rates, is from Asela and Shapira, at least for this thing about covering a macroscopic set, which tells me that, tells us that if we want to cover, I think Bruno also mentioned this one result in his talk, if we want to cover a set of balls, for a macroscopic fraction, each of them, then this probability converges to 0 exponentially fast with a cost, with a speed, which is of capacity order. And then there are some uniform universal constants here. Of course, this result is nice because it is non-asymptotic. So it's a super cool result, but we look actually for taking R to infinity with n, and for exact asymptotic rates. Okay. Let me mention this work by Xin Li that is very much connected to what we do today. So in this work, which goes back to 2017, 2014 for the upper bound, Xin Li and Snitman were looking at the following event. They were looking at the probability that the random walk disconnects a macroscopic body from infinity. And also in this case, if you want to disconnect this body from infinity, you need for the walk to spend a lot of time around the boundary and to come back many times. And then also, you will see that around the boundary, you have some atypical high density regime. And in fact, what they used in order to derive upper and lower bounds are couplings with random interlacements. in fact, the picture is not entirely correct. This is not the optimal strategy. And we will see the optimal strategy to realize our bias deviations. It will have to do also with the optimal strategy for this situation. So the result that they get is that if we want to disconnect a macroscopic body from infinity by the simple random walk in dimension d greater or equal than 3, then this probability goes to 0 exponentially fast with a speed which is of capacity order, so n to the d minus 2. And with a rate which is very precise, we have the capacity, and this is the Brownian capacity, of course, because we are homogenizing, so to say, the simple random walk. This is the Brownian capacity of the model shape D. This is just a factor that keeps into account the microscopic structure of the lattice, so the simple random walk variance on the lattice. And then we have this U star that was not mentioned in this way this morning, but this is the critical parameter for percolation of the vacant set of random interlacements. And so what you see here is that in deriving this probability, what enters in the game are crucially parameters that are connected to random interlacements. I have to say that in the work by Xini Li that derived the lower bound, this was not U star, was U star star, another parameter, but very recently it has been shown sharp phase transition for the percolation of the vacant set of random interlacements that allows us to apply those results and get exact asymptotic rates. Okay, so this was to show you that random interlacements will enter the picture. In fact, also here, let me mention that you have the Brownian capacity of the set D. So if you think about it, the minimizer for the variational problem associated to this capacity is the harmonic potential of the set D, right? So what you will have is that for the walk to disconnect, it will also need to cover inside, to have a density inside. Okay, so it will cover everything. Okay. We got a mini course about random interlacements, but I think it's still a good idea to go over the definitions once more. I will be quick anyway. So random interlacements at a certain level U. It's a Poisson point process of doubly infinite continuous simply random walk trajectories. And the way I like to describe it, and this is also the way Alexis described it, is by looking at the local picture. So if we want to sample random interlacements inside a finite set, we argue as follows. We sample the number of trajectories, of random walk trajectories as a Poisson random variable with parameter U times the capacity. And now this is the random walk capacity of this set here. So for example, we sample two points, and then we choose those 2 points on the boundary according to the equilibrium measure of the random walk. And then we just sample independent simple random walk. And this gives us the interlacements inside the set, SC. And what turns out to be is that you can construct an infinite measure, and so you also have a measure on the whole ZD. And this gives you a kind of a global picture as the random interlacements as a Poisson cloud of walks. Here I like to have this Poisson cloud of walks both in the space of trajectories and the space of labels, as this makes a nice, you are able to construct interlacements for all intensities in this way. And just by increasing the intensity, you are just throwing more trajectories into the space. Right? So this was the crash course, and I did that because I needed just this object here that will be crucial in our derivations. And it is the occupation time field for random interlacements. So we call LXU the total time spent by the trajectories of random interlacements at level U in X. And we saw the interlacement set these days, and it is just a set of points, is a random set where the total local time by random interlacements in those points is positive. So it's the set of points visited by random interlacements. We also saw this characterization, which completely uniquely characterizes this random set, which is the interlacement set, that tells you that the probability of non-intersecting a certain k finite, it goes like exponential minus u, the random walk capacity of this set. In particular, the probability that 0 belongs to the interlacement set at level u, it is given by an exact formula, and it is 1 minus exponential minus u, the capacity of 0, which is 1 over the Green function at 0. Okay, let's go back to the problem of understanding large deviations for this, event here, that we cover a positive fraction of a macroscopic body in dimension d greater or equal than 3. So let me recall you, we have some model shape D. We look at its discrete blow-up, and we have some fraction of points that we want to cover by simple random walk inside here. And the goal is to find the exact, precise large deviation asymptotics. Since the random walk is realizing very atypical high densities in order to, for this event to happen, then the idea is going to be to study first large deviation estimates for the interlacements, and then hopefully go from there and derive the result for the random walk. So we first study the event that the random interlacement set at level U covers a positive fraction of points inside of this macroscopic body. Okay, this is not a result that we obtained. This is from Snitman, and it goes like follows. Well, first notice that the random interlacement set is a nice stationary set, and it is ergodic. So if you look at the number of points inside of macroscopic body, by the ergodic theorem, this is just a probability that 0 belongs to this set, right? And so it is the expected density is exactly equal to 1 minus e to the minus u over g. And those of you that are familiar with the work of Vanderberg, Bothausen, and then Hollander will recognize this, this function here. I will come back to this later as well. So we look for excess deviation. So let's take this fraction here to be bigger than this density. Otherwise, this event is not rare. And then the question is how fast this guy goes to 0. So how do interlacements look like conditioned on this event? Okay, this is a theorem by Snitman, and it is from 2019. And here it is a nice theorem because you get the exact asymptotic for this rare event here. So take any fraction bigger than the average density of random interlacements inside the set Dn. I call this function theta u. Okay. Then you have that this probability converges to 0 exponentially fast with the rate, with the speed, sorry, which is of capacity order, n to the d minus 2, and with a rate that it is precisely described by this variational problem. So what is this variational problem? Here we are just minimizing the Dirichlet energy. You can think of this is the Dirichlet energy of the Brownian motion. Okay. Over all functions that are non-negative, smooth, okay? And what we want is the following constraint to be satisfied. So we want that the average over D, this line is just to say that we are taking the average, of theta computed in square root of u plus phi squared is above the fraction nu. This is the variational problem.
So it is not square root of 2u?
No, it's square root of u. Yes. If you are thinking about the Gaussian free field, in a way, a similar result can be also obtained for the level set of the Gaussian free field. But instead of having a square here, you are going to, there will be no square, and the function theta is not this one, it's another function. But it is going to look pretty much the same. Okay. Okay, nothing happened. Okay. So what is going on? So we have, since you have both upper and lower bound, typically the lower bound you find it by constructing a suitable strategy. What is going on is that this deviant behavior is realized as follows. So random interlacement, you have the random interlacement, so it's this family of random walk trajectories, right? So what you do, you take each one of these trajectory and you tilt it, you add a drift to them. So, and you tilt it by as follows. You take the minimizer of this variational problem, here, and you tilt it essentially by the gradient of the log of square root of u plus the minimizer. So it's the usual H transform. But for random interlacements, of course, you have to apply it to each and every one trajectory. And so this already tells you something interesting, and that is that the density of random interlacements will be large inside. It will decay also outside, and it will always stay above U. Okay. How do we use this to get a solution, an upper bound for the random walk? This is, so the hard part of what I'm saying now is a Snitman result. Okay. Now to get an upper bound for the simple random walk is going to be easy. Because what we do, we just take the intensity parameter of random interlacement to 0, and in a way this leaves us with only one trajectory, right? If we condition that at least one point, the origin, for example, belongs to the interlacement set. So if you go back to the previous problem, here, and you take u to 0, so to say, to remain with only one trajectory, then you have a guess of what is the rate for the simple random walk. So this is exactly what you get here as an upper bound. So the probability that a random walk started from the origin is not important, it is the origin, of course. That the random walk covers a positive fraction of the macroscopic set dn is at most minus this rate function here. The speed of convergence to 0 is still of capacity order, and this rate function is just the minimization of the Dirichlet energy constraint over all functions u that are non-negative, constraint to the following constraint. And look, this is just coming, this is just a function theta u, theta computed in phi square. So to understand what happens to the random walk, we brought in the random interlacements in a crucial way. This is, okay, I wanted just to mention that this has some connections with the Wiener sausage and the Swiss cheese picture by Van der Berg, Bolthausen, and Den Hollander. In that picture, you had a Brownian motion, and then you look at the Wiener sausage associated to it. So you enlarge, you look at the R neighborhood of the Brownian motion trajectory. you have a law of large numbers that tells you that the size of the Wiener sausage divided by t converges to the capacity of the ball of reduced R. And then they were not looking at excess deviations, but defect deviations, but what they get is a very similar behavior. You have to think about that in their case, you have a finite time horizon. In our case, the random walk goes for all times, right? So what for them is t, for me is n to the d. And then you get exactly 1 over n to the d minus 2. And then this variational problem. And this function is exactly the one that comes from random interlacements. So that's the picture you have to have in mind. And there is just this extra constraint that is due to the fact that we don't have a finite time horizon. So this is just to impose a finite time horizon in a way. And of course, this integral is not over d, but is over the full space, because we are not localizing over a macroscopic set in this result by Wieners, by Bolthausen, Den Hollander, and Van der Waal. Okay, so there is this kind of similarity. Let me give you a 3-line proof of the result, the upper bound, because I think it is simple and nice. So let's look at the interlacements with intensity u. And let's condition these interlacements to contain the origin. Why? Because this way, if we just look at, there will be some interlacement trajectory going through the origin. The forward part is just a simple random walk. And so we can dominate the probability that the random walk covers a macroscopic body of the set dn by the probability that the interlacement set covers a macroscopic part of that body, conditioned to 0 being part of the interlacement set. And now it's just a matter of simple computation and using the Sneedman result for the large deviation events for the random interlacements. Just notice that the probability that 0 belongs to in the interlacement set is of order 1. And so it goes to 0, it doesn't really matter. And so you have a very simple upper bound by domination for the random walk by the same result for random interlacement. Then what is left to do is to take the intensity to 0 and get the upper bound for the random walk. Okay, what we did together with Maximilian is to derive a corresponding lower bound, which is normally which is a bit more complicated than what I just showed you. And so what we are able to say is that, in fact, for the simple random walk, the probability to cover a macroscopic fraction of dn, it goes to 0 exponentially fast with speed n to the d minus 2, and with a rate, which is the one that I showed you before. So this minimization, this variational problem. Okay, in order to get this lower bound, we need to produce a suitable optimal strategy to get the deviant event. And for that, we follow a similar path as Xini Li did in his work in 2017. And so let's go there. I put this because I like this this general principle for deriving large deviations lower bound, which is just the change of measure method. It's very simple, but it's so nice that I put it. So we want to get a lower bound for this deviant behavior. Okay. So what we do is we use the following entropy inequality. So you have to think of P as the a priori measure, so the P0, the simple random walk measure, and then we want to construct a new measure, a tilted measure, and this will have a cost. And we'll have a cost of the relative entropy between Q and P. And this entropy inequality is pretty general, but you see on the right-hand side, you get the log of QC divided by PC. So you just reorder stuff. And so you are able to find a lower bound on the log probability of any event by the log probability of any other measure that is absolutely continuous with respect to P by paying the price of relative entropy. Of course, now it's a question how you choose, how you construct this Q. This is where you want to have an optimal strategy, because you want the QC to be 1, essentially. So you want a new measure that makes the deviant event typical, and you want it to be computable. These are the two things you want. So the core idea is to construct then a tilted measure, P tilde n, which you can think about if you come from stochastic control. I don't think so, but if you think about that, it's just you want to add a control to the random walk via, for example, an H transform. In order that under this new measure, the event that we are looking at becomes typical, and so that the relative entropy, the entropy cost in changing the measure is easy to compute and nearly optimal. And if you do so by applying the relative entropy lower bound, this first part is just going to 0 because Pn an is going to 1, so this is typical. This is going to 1. And so what you are left is just the relative entropy. So what is this nearly optimal strategy? We cannot do exactly as we did with random interlacements, just add a drift and we are done. Because if you do that, the random walk becomes recurrent. Okay? And so you are not going, it's going to be too expensive as a strategy. You don't want to fill everything. You just want to fill up to fraction nu of the full body. So instead, you do something as follows. You stop the control. So you add a drift, but just up to a certain time, Tn. I'm going a bit too fast. Let me see. Anyway, so let U be a minimizer of this variational problem. Of the variational problem associated to the rate I showed you before.
So we know there exists this minimizer?
Yes, yes, yes. It exists because the function, okay, the function theta u is a nice function. It's even C infinity, in this case of the range. And so by standard, you are minimizing the Dirichlet energy, which is convex. So by standard, the lower semi-continuity of the Dirichlet energy, you get the existence of the minimizer. What we don't know if it is unique, and that's much more challenging. So there exists a minimizer of the variational problem. Of course, we want a minimizer that is smooth. So there are some technicalities involved to take a quasi-minimizer that is smooth. Okay. And also we wanted to have some zero boundary conditions, so there is also some cutoff involved. But let's think intuitively. So let's U be a minimizer of this variational problem. And let's us introduce a certain time horizon, Tn. And Tn is n to the d, the L2 norm of U. So you see, when I said before that in Vandenberg the L2 norm was there because we had a finite time horizon, you have to think that is here where you see that. Because if you take U and it has infinite, a finite L2 norm, then you are just stopping at Tn to the d. So you stop at this time, and then you might ask, well, but how you know that this function is as a finite L2 norm. Well, this is where we say, well, let's first cut off, let's take a very big radius, and so on. And it will turn out, and I will come to that in a second, that in dimension 3 and 4, even if you do the cutoff as r goes to infinity, this will explode, while in dimension 5 and higher, this is finite for the minimizer. So there is an interesting regime in dimension 3 and 4. So the idea now is, well, you take a random walk with a generator given by as follows. Okay. So if you like it more, it is just an H transform of the random walk through this function here. And if you like stochastic differential equations, this is like adding a drift, which is the gradient of the log of this new potential. Yes?
Is U harmonic?
U is going to be harmonic outside of Tn, of D. Because I will come to that then. I will explain more. Yes, U is harmonic outside of T, but not inside of T.
So this is not exactly a dimension.
Not exactly, but it looks like. Yes. You are adding a drift by the gradient of the log of a potential. You have this control. So it's not harmonic everywhere, but outside of this set, it is going to be harmonic. Okay, you add this drift up to time Tn, and then you release the random walk. So you push it to stay inside, in a way, by this minimizer. It will fill up this set, but not only this set. You have to realize that, in fact, it will also spend a lot of time around it. So the density of the random walk around this set will be positive everywhere, actually. And then it will spend some time here up to time this Tn, and then we release the random walk. And so after this time horizon capital Tn, we will let it evolve just like simple random walk. So it will escape to infinity eventually. Denote by P tilde n this strategy, and the claim is that this is the optimal strategy. Well, it's one of the optimal strategies, because we don't know uniqueness, there are some things open. So let's think, I will give just some heuristics for why this works. Well, first, the way this strategy is constructed allows you to compute essentially exactly the relative entropy cost of this strategy with respect to the a priori measure. And it is just going to be the Dirichlet energy of the minimizer plus something that goes to 0 as n goes to infinity. So this is good job one done. Find a tilted measure for which the relative entropy is easy to compute. And then what is important to realize is that under this new strategy, we are actually able to cover a positive fraction of the random walk of the set Dn, a fraction nu. And here I'm going to argue a bit heuristically by saying that under this strategy, we are adding a drift that makes the random walk comes back many times to itself. And so it locally looks like random interlacements with intensity given by this u at, well, x over n. U is a macroscopic function, and then you put it here, for example. So we have a strategy by which this tilted measure looks like random interlacements with intensity u. This is good. And so we argue now as follows, that to show that this this event here is likely under this strategy. We take the range of the random walk, intersected this macroscopic set, dn. And then we divide it into many mesoscopic boxes, B. They need just to be slightly smaller than the scale n, not too much. And then this, by this statement, of course, this has to be, this is where part of the proof becomes a bit messy, but you have that this quantity here now in distribution is very similar to sum over all these mesoscopic boxes of interlacements at the level uxb over n, where xb is one center of these boxes, intersection B. And then this is just the law of large numbers for the interlacements that tells you that, and we saw this in the beginning, that this quantity here is roughly theta, since this is interlacements at level ux beta over n. This is theta u square xb over n. But you see, we just chose this minimizer in such a way that its average over d of theta computed in u square is equal to nu. So this is just a Riemann sum approximation. This is nu, the size of the set dn. And so after this tilting allows you to construct a strategy for which the range of the random walk inside dn is roughly equal to nu, the size of the set. Other questions on this? Yes?
Just to understand, because this large deviation functional is basically the Donskervard functional for the local time.
Yeah, yeah. Essentially, yes.
So what is really the difference with the setup that you would do?
Well, there is an infinite time horizon first. And yes, you are restricting to this set here, and then you want you have this high density regime, which is quite important. So we want really the local time to fill up this set up to order n to the d, and this brings into play the random interlacement. Otherwise, you wouldn't really see too much. You would see it at a different scales. I don't know if this is.
So the u square is because that's u square is the density.
U square is the density. Yes, u square is the density. Okay. Any? No. Maybe later. Yeah, a couple of remarks on the methods of the proof. The construction of this strategy is a generalization of the tilted walks by Lee in 2017, where in this case the minimizer was the harmonic potential of the set dn, so it is constant inside of dn. And in our case, the minimizer, of course, is the solution of this variational problem that a priori we do not know whether it is smooth or anything, or whether it is unique. And it is also, of course, what I cheated in these heuristics is that I said to you that on mesoscopic scales, since we have these high density regimes, the random walk looks like random interlacements at the level u square. Well, there is some work to do there, right? And here we need to couple the local time field of the tilted walk with that of random interlacements at these mesoscopic scales. And here we generalize our construction by Windisch and Teixeira and Lee, as we do not just couple the traces, but we need also to couple the local times for the more general statement that I mentioned with this function f. Let's come back to that statement. So if you have a certain range of inspection, so if now your function here, your local function of the occupation time field of the random walk is not just the indicator that the local time is positive, but is any function with finite range of dependence, and it is 0 and 0 and non-decreasing. And then there is some sublinear growth assumption as well. Then the same proof will lead to the result, to a very similar result. So we look at the averages for these observables, for these local observables. And now the function theta here, crucially, is the expectation of f computed in the local time of random interlacements at level u. So if before it was 1 minus e to the minus u over g, now it is a certain function that comes from random interlacements as follows. And let me tell you that the same proof will give you the asymptotic lower bound. For the upper bound, this is still due to Sneedman. And he proved the upper bound for random interlacements, and you just take the intensity to 0 to get the upper bound for random walks. And the theorem is that for any nu which is positive and below this, the limit as u goes to infinity of this function here, you don't want to saturate this function. Then the probability that you get a deviation from the expected behavior, which is 0 as n goes to infinity, goes to 0 exponentially fast with speed n to the d minus 2, so still the capacity, and with rate, which is exact, and it is this variational problem over here. So it's a minimization problem. Okay, we have a minimum here if you relax if you take a larger set of functions where you minimize. So it's a minimum over all of the Dirichlet energy over all non-negative functions that vanish at infinity in a weak sense, and constrained to have an average over d of theta phi square equal to nu. And so this phi square, if you take the minimizer squared is the intensity of the random interlacements that you see in the behavior of the random walk to achieve this deviant behavior. Okay, a couple of words on the variational problem. So the variational problem, which gives you the rate, is the following. So you want to find the minimizer of the Dirichlet energy subject to a certain constraint here. You can prove under the assumption we have on f that theta is Lipschitz. It's not necessarily differentiable everywhere, though. And but suppose that it is Lipschitz differentiable. Okay, suppose u is a minimizer, then it is just a simple first variational calculus to show that this minimizer needs to be harmonic outside of the set D. Okay. And since it is harmonic, also since you can show that it is positive inside of D in many situations, then it has also this decay here. So it decays to 0 as x to the, like the green function, x to the 2 minus t. And it is also bigger or equal than x to the 2 minus t. In particular, this tells you that the L2 norm of this u is infinite in dimension 3 and 4, and it is finite in dimension 5. So if you go back to the thing about the optimal strategy, in dimension greater or equal than 5, in fact, you do stop after a time that is of order volume, n to the d. But in dimension 3 and 4, yeah, we stop because the technique of the proof, but you need to think that we were taking this big ball cutoff. But in fact, this quantity will blow up as the cutoff is removed. So in a way, in dimension 3 and 4, the random walk needs to come back much more, for a much longer time. It's not clear exactly if it is an infinite. Possibly, yes. It would be nice to quantify this behavior a bit better. And the other nice thing is that, of course, this is a minimization problem, so you can look at yes?
Can you clarify in which space you're minimizing?
Sorry?
In which space you are minimizing?
So this space is the space of functions that vanish at infinity, that have Lebesgue measure that vanishes at infinity and have finite Dirichlet energy.
But they have some smoothness.
Yeah, but I don't ask them to be in L2. So they have just finite Dirichlet energy. So this doesn't imply that they are in L2. Okay. And they need to vanish at infinity in a weak sense. So if you look at the measure of where the function is bigger than than A, this needs to go to 0 when you take A to infinity. Okay. The minimizer is smooth outside of D. The fact that it is harmonic gives you smoothness right away. It's infinity outside of D. Right? Every harmonic function, it's infinitely often differentiable. Once you know that you have vanishes at infinity. Okay. And there is this dual way to characterize the minimizer via Lagrange multiplier. Of course, you need the theta to be smooth. And this is a very terrible nonlinear problem. So you see here I have also the indicator of the set D, which was my model shape. In particular, you have that the function is harmonic outside of T, but then it needs to solve this semi-linear PDE inside of T, and it's not clear that the solution is unique. A uniqueness for this kind of problem has been shown recently for the Wiener sausage case by Poisson and Dirk Herrad, but they have D equal the whole space, and that they can use the translation invariance essentially of the problem to get uniqueness. Okay. Let's see in the last couple of minutes an application that is not the range. So let's look at AN to be the number of points in this big box, Dn. Could be anything, it needs to be macroscopic. And the number of points that are disconnected by simple random walk from infinity, we want this to be a positive fraction of the whole set. And then this will bring into play the percolation function of the vacant set of random interlacements, which is this theta u, which is not even clear that it is continuous around the level for percolation. And you look at the right continuous modification of this function. Okay. Then what this result that we have with Maximilian tells you is that the probability of this event goes to 0 exponentially fast, like n to the d minus 2, and the rate is completely characterized. And it involves this percolation function for the random interlacement, for the vacant set of random interlacements at level u. The lower bound can be achieved by using as a function this fr, which is I just looked whether 0 is disconnected by the range of the random walk from an enclosing box, and then I get a lower bound for each r. I take r to infinity, and I will get this rate here. And the upper bound is much more complicated, and it is due to Sneedman in a paper in Invenciones, 2024, and he was mostly interested in the random interlacement case, so you still need to take u to 0, plus the equality of the critical parameters, plus the sharpness of the phase transition for percolation of random interlacement. That is also something very new by Domenico Pango, Swami, Rodriguez, Severo, and Teixeira. I think this is all what I wanted to say. Thank you for your attention.
Okay.
like a large deviation principle for this
Square of the GFF. Is there a way to derive
results out of the by using isomorphism theorems and applying what is known for Gaussians?
I don't think it is so easy. So I think you might get guesses, good guesses, but it is not so easy. In fact, you can start from here and also get a guess for the GFF as well.
Tuning of GFF is much easier than this case where you just sort of tune them.
So one of the bounds one might be easy, but yes?
The behavior or the random walk behavior you construct for the lower bound, you also expect it to be typical? Did you condition on that?
This is a very good question. I expect in some way to be typical, but then you don't know whether the minimizer is unique. So there might be other, behaviors that are also typical. And then there is also a question of, we add the drift immediately, right? But you could also add it later, and as long as you add it for a sufficiently long time. So it should be typical in a certain sense to be clarified.
What about smaller densities?
Yeah.
Going to zero. You have all the moderate deviation. Can random interlacement helps you if the density goes to zero? But
yes, so not dividing by the volume, but by smaller. Yes, but I think, it will help you, but it changes the nature of the problem in a way, because it goes more into the direction of that you don't even see the dn anymore, right? You don't see the macroscopic set anymore. If you need to cover a fraction that is much smaller, you just cover it close by, and then you lose the. So it's not super clear in which way it will help you actually. It should still. I still think you will see random interlacements where for covering, but.
And there was a second problem in the Volthausen friends paper, which was the intersection of two walks.
So
can you do it?
So here Chiarini maybe has more, because he looked at the intersection of two interlacements, and he derived very precise bounds there. And I don't think you did take U to 0 though. So it is just for random interlacements now. So the upper bound for random walks should be doable, easy. The lower bound, one is maybe to work with this kind of techniques, yes.
I wanted to ask a question. So if you are looking at the time of the last visits to the end in dimension 3 and 4, do you have a conjecture for?
I didn't think about it, but it's a very good thing to think about. Yes, thank you.
Okay, if there's no further questions, let's thank Alberto.